Hi everyone, welcome back to my channel. This is Xiaofu, a research scientist and enthusiast on control system and its related algorithm development. Right now I'm working as a control engineer at a semiconductor company, and on the side I'm also doing my own startup on energy harvesting. If you like my YouTube channel, please feel free to subscribe. In this lecture, we are going to discuss the Caley Hamilton theorem to derive system properties from state space representations. And in the next lecture, we are going to look at the relationship between state space representation and its transfer functions. Okay, so let's have a quick recap. We know that a nonlinear system, its dynamical response can be quickly represented by state space representations, which means x dot equals to ax plus bu, y equals to cx plus du. Generally, d equals to 0, and x is actually a bunch of first order differential equations. And the number of those first order differential equations depends on how many states you have. Okay, so after you have these state space representations, if we give you an initial condition and define the input u, can we derive or deduce the system response, right? Which means the solution of the state space equations. And after that, there are some other properties such as stability, characteristic oscillation frequency, time constants, statistic response. And if we have a full understanding of the system dynamics, that means we can design a corresponding controller. Anything that you have no idea on your system dynamics, it will be a black box, right? So if you know or better understand your system dynamics, then your controller can be much simpler and also easier to be designed. Regarding the system response, it has free response and also forced response. Generally, free response will quickly converge to 0 because of the damping. And so you give an initial condition and then you don't apply any other force after that, so it should converge to 0 eventually. So let's start with unforced response. Let's define a simple system, x dot equals to ax, which means you don't have inputs u over there, so that's why we have free response. And if you give this a initial condition x0, let's compute x of t. So we can use a simple math equation dx over dt equals to ax. So that's very simple. People who have already gone through these advanced mathematical classes during bachelor degree should have a good understanding how we can derive that. So if you look at it, so your x of t will eventually equals to e to the power c times e to the power a times t. So which is an exponential decay system if you have damping over there. And that initial condition will give you a starting point, so where your system is slowly decay to 0 in an exponential way. So here, after we have look at the unforced response, but if we have b times u that is added to your state space representation, then you have a forced response. If you're given an initial condition, then how can we compute x of t as a function of u, right? Suppose u is a non-zero constant, but for what values of a does x of t approach some constant value, right? Those are the questions that we might need to ask to understand the characteristic of the system. But how does the time constant of the system response depend on a? But what about how do the threshold value of a relate to the threshold values we found for the free response? So let's say we right now derive a theoretical equation for your free and also forced response that you can see at the final results. So x dot equals to ax plus bu. You move ax to the left hand side, and then multiply e to the power minus at on both sides. This is just a simple trick which we can solve the differential equation quickly. So if you look at this one is essentially e to the power minus at times xt is derivative with respect to time t. So similarly, that you can do is you can do the integration or integral on both sides with respect to t, where tau can be considered as another time variable. So 0 is the starting point, t is your final time point. So if you look at it, so you can solve your integral very easily by substitute t and also 0. So where you will get on the left hand side, you will get e to the power minus a times t times xt subtract by e to the power 0, which is 1 times x0, which is your initial condition. If you multiply e to the power a times t on both sides, so you will get x of t on the left hand side subtract by e to the power a times t times x of 0. The reason why we might multiply by e to the power a times t because we want to express x of t explicitly. So if you move that to the right hand side, you get this final equation. So where this is depends on your initial condition, and at exponential decay, this is your free response. And the other one, which you have u tau, which is your input that give you the forced response. So any system dynamics can be expressed by free response plus forced response, or you can consider transient response plus steady state response. So if we keep going, for simple system x dot times ax plus bu given an initial condition, we just derived that formula just now. So that's not that difficult. Well, what about you have a higher order system where your a is no longer a constant, might be a matrix, right? So then there are some critical questions we need to ask. How do we compute e to the power a times t where a is a matrix, right? Or what properties of a can we look at to answer the same questions about stability, time constant that we answer for the first order system based on a constant small letter a. So that's the reason why we introduced Caley Hamilton theorem. That's the one that helps us to solve the matrix exponential. So a matrix A satisfies its own characteristic equation. So this is a determinant of lambda, which is defined as a characteristic polynomial, where lambda is the eigenvalue of the A matrix or of your system. So it's actually the determinant of lambda I subtract by A equals to 0. So characteristic of delta lambda equals to 0. So you can express this equation as lambda to the power n plus a n minus 1 times lambda to the power n plus 1 until a first zero order term a0 equals to 0. So this lambda n depends on the number of states or how many eigenvalues you have for your system. So similarly, Caley Hamilton want to mention here is a matrix A also satisfies its own characteristics, right? So lambda for sure we know is the same thing when we derive the characteristic equation for eigenvalue. So if you consider this is not lambda is A itself, so you can write the same equation also let it equal to 0. So this satisfies the same thing. Maybe this one is a little more complex, but let me make it easier to understand. So if you move on to the later slides, I will explain. So let's say right now we are supposed to get the matrix exponential. As we just mentioned, a function of A. So any polynomial in A can, no matter how higher order is, can be written entirely in terms of A, and also its higher order itself, right? So then we can consider e to the power A times t is the f of A here, and if we mimic that, so what we get is for zero order all the way to higher order of A, which is n to the a to the power n minus 1. So similarly, as we mentioned, the lambda is all satisfied for sure its own characteristic equations. So, but the constant here, alpha 0, alpha 1, alpha 2, those coefficients are indeed using the same coefficients, since we can simply solve lambda based on the eigenvalue, right? So that's why the first step is compute eigenvalue of A. After you get lambda, you can use equation 2 to solve alpha 0, alpha 1, those coefficients, and if you substitute in 1, then you get it, right? You get it for your matrix exponential. So Caley Hamilton theorem said, okay, a matrix A also satisfies its own characteristic equation, which is the one that explained here. Okay, so as we know, this is the characteristic equation for the lambda. When we derive lambda, this term equals to 0, right? So if you look at Caley Hamilton theorem, so P of A, or no matter use P of A or F of A, equals to Q of A. This is the one that we just mentioned, as it is also 0, so you get R of A only itself. So that's why you have those alpha 0 plus alpha alpha 0 plus alpha 1a all the way to a to the power n minus 1. So let's look at some examples to help you better understand how we derive the matrix exponentials. So right now, since we simply list out those steps, step 1 is looking at the state space representation. We firstly derive the eigenvalues, right? So then the eigenvalue of this state space representation can be considered as lambda I subtract by A, the determinant equals to 0, and we derive lambda 1 and lambda 2, which is minus 1 and minus 4. And if you go back to look at this equation we listed out, so it is, okay, so e to the power lambda I t equals to alpha 0 plus alpha 1 times lambda I, right? So let's say your lambda, so right now, okay, if we go back, as here we only have 2 by 2 matrix for A, so which means n equals to 2. If you go back, if n equals to 2, so n minus 1 equals to 1, right? So we only should have alpha 0 plus alpha 1 lambda I. So let's come back. So that means if you plug lambda 1, which is minus 1 e to the power minus t equals to alpha 0 plus alpha 1 lambda 1. Similarly, we also have lambda 2, so 2 equations, 2 unknowns, so which you can solve alpha 0 and alpha 1. So if you solve alpha 1 and alpha 0, you can substitute into equation into the power a times t. So which is alpha 0 times identity plus alpha 1 times a, right? So since we've already know what is alpha 0 and alpha 1, we also know what is a, so you can definitely get the matrix exponential, right? That's not difficult. So that's step 1. But why we need this exponential, matrix exponential? Because if we go back to the equation that we just derived, as you can see, how do you derive a system response for higher order system? You need this e to the power a times t, right? Free response and also forced response. But you also need to know your B matrix and also your input U. So let's keep moving on. In the following examples, we will have it. So right now, okay, so since we derive e to the power a times t for system 2 already, and let's wait a sec and let's start with a simple example, which is a very simple first order differential equation x dot equals to minus 2 times x plus 4u, where your initial condition equals to 0.5. And for system 2, we take the input u of t equals to 1, right? So small letter a equals to minus 2, small letter b equals to 4, right? Let's use this equation. So let's okay, so start from system 1 or example 1. So if you look at it, so you will realize our initial condition that we defined as 0.5, we can also substitute into this formula. A is minus 2, as we already saw that. So which means your free response equals to 0.5 times e to the power minus 2t. And your forced response, we know your b equals to 4, your input u equals to 1, as we just mentioned in the predefined requirement. So we can simply derive it. And also we said that, okay, the final time is 10 seconds, right, from 0 to 10. So you can use your final t equals to 10, and finally you will derive this final result for this first order differential equation system. Let's look at this more complex one, which is a 2 by 2 matrix for A. So A is no longer a constant. So, but still, the equation doesn't change at all. Instead, your A becomes a matrix just instead of a constant, right? So we know your initial condition for those two states, x1 and x2, equals to 1 and 0. And when you derive your system response, you should also derive that for x1 and x2 separately. Recall this equation. Our initial condition, which is 1, 0, and our B is 0, 1. Let's go back, just in case you forgot, our B matrix is 0, 1. Okay, so then we also just derive e to the power a times t from the example just right before this. And our free response is very simple. We use this matrix multiplication, we get this free response. And for the forced response, it's also not that difficult, but a little bit more complex, but you just need to do a bit more math operation. So we know that our u of tau, let's say equals to 1, since we've defined that. So you can simply put 1 here. So our forced response can be considered, let's say, your e to the power a times t we know is here, but right now use your small letter t and substitute with bracket t minus tau, and you get e to the power a times bracket t minus tau. Since you are multiplying by 0, 1, so that means you should only have this this second term here, which is 1/3, right? And you should also have this second term here, right? Since this is 0, 1 for the B matrix. So where you get your forced response representation. Well, we also know that your tau starting from time 0 to times 10, right? So if we do that, we get x1, x2, those forced response very easily. So now you are able to derive the system response for simple first order system and also more complex higher order systems, such as the one we just did, the second order system, where your A matrix is a 2 by 2 system, right? So if we look at it, how the system response look like for the example 2 we just did. So response of x1, so we have free response, which is the blue dotted line. As you can see, free response, because of the damping, it should eventually converge to 0. But as your forced response, since your force is a constant, so it should eventually converge to a constant value. And so, which is your position, right? This can be considered as a position for x1. And if you add them together, you have a final full response, but still it should only converge to your steady state whenever your free response decay long enough with the time constant. So let's say after 6 seconds, you actually decay. So if we go back to the system, we say the A is 2, right? Minus 2. So generally the tau is actually 3 times this A value, which is 6 seconds. So as you can see, after 6 seconds, your free response almost decay to 0. So that's your time constant. Okay, so let's summarize. So right now, we come up an expression for the system response for x of t, as we just derived, free response plus forced response, of course, yes. And can we use this expression to deduce important system properties such as stability, time constants, which we will address this in the next 2 lectures. Okay, thank you everyone for watching my YouTube video. See you next time.